This project analyzes what fundamentally changes when MRI is done at 64 millitesla, as in the hyperfine portable scanner. AIM-1 shows that low B naught alters relaxation and susceptibility, meaning T1 shortens, T2 star lengthens, and susceptibility and chemical shift artifacts shrink. SNR becomes coil noise dominated, breaking the usual B naught squared intuition. AIM-2 shows that weak gradients and limited sampling impose a hard resolution ceiling, since K-space coverage is strictly limited by G in readout duration. AIM-3 explains why modern reconstruction, regularized parallel imaging, and deep learning is essential because low SNR and sparse sampling make the encoding matrix poorly conditioned. Overall, portable MRI succeeds by exploiting a different relaxation regime and compensating hardware constraints with reconstruction to deliver clinically useful bedside imaging.
Hello, everyone, and welcome to our presentation on portable MRI and analysis of low field constraints and opportunities. To start, for this project, we're not only talking about theoretical low field MRI, we're specifically interested in modern portable systems like the hyperfine swoop depicted here. These operate at about 0.064 Tesla or 64 millitesla. They use permanent magnets and are designed primarily for bedside brain imaging in ICUs, emergency departments, and other environments where moving a patient to a fixed scanner is dangerous or logistically impossible. So, our project asks a single overarching question, which is how does dropping B naught by nearly a factor of 50 fundamentally reshape MRI physics, encoding, and reconstruction? And what does that make portable MRI uniquely good at and uniquely bad at? To answer that, we break the problem into three aims. Aim one, we look at how low field physics reshapes relaxation, contrast, susceptibility, chemical shift, and SNR scaling. Aim 2, we look at why portable systems cannot use conventional gradient encoding and how low G, low slew rate, and low ADC sampling impose hard limits on K-space extent and spatial resolution. And in Aim 3, we'll look at why low SNR and sparse sampling forces reliance on modern reconstruction and how low field hardware worsens conditioning and G factors. Together, these aims let us understand portable MRI not as a worse 3T, but as an imaging modality that lives in a different physical regime with its own constraints and opportunities. So first, dropping from 1.5 Tesla or 3 Tesla to 0.064 Tesla seems disastrous for SNR if you only think about M naught. But low field also reshapes relaxation in ways that matter. T1 shortens substantially as B naught decreases. McGrath and collaborators show this clearly across multiple tissues here. So portable systems can use much shorter TR and recycle magnetization more efficiently despite lower M naught. Meanwhile, T2 is fairly stable, but T2 star increases dramatically because susceptibility-induced delta B shrinks with B naught. McGrath's simulations show orders of magnitude longer T2 star at low field for the same inhomogeneity. The takeaway is that low field MRI lives in a distinct relaxation regime. Shorter T1 and longer T2 star allow short TR sequences and longer coherence windows, meaning 64 millitesla is not just 3 Tesla but worse. It's a fundamentally different operating point in the block landscape where the dominant relaxation processes and contrast mechanisms are different. Also looking here at susceptibility and chemical shift, MRI is changed in low field because susceptibility-driven delta B scales with B naught. The static dephasing term in T2 star becomes much smaller. Clinically, this means that there's less blooming and less geometric distortion near air-bone interfaces or metal. And Kimberly and their collaborators in their papers show that some low-field brain images are actually geometrically cleaner despite being noisier. But the flip side is that contrasts that rely on strong susceptibility differences, like susceptibility weighted imaging or high resolution bold, become much weaker at 64 millitesla. So portable scanners rely more on T2 flare, as hyperfine documents show. Chemical shift behaves the same way, where delta omega is proportional to B naught. The fat water frequency difference collapses at low field, reducing classic artifacts, but also making fat suppression and Dixon separation harder. Overall, low field removes many artifacts and gives cleaner geometry, but at the cost of losing some high field susceptibility-based contrast. And then finally, we can look here for SNR. The usual story is that M naught scales with B naught, and in the sample noise regime, SNR often goes like B naught squared. So that would make 64 millitesla look hopeless in terms of imaging, but McGrath and collaborators also showed that once you model coil noise, field-dependent T1, T2, T2 star, and realistic TR and T, the scaling bends away from those simple power laws. So at low field, systems become coil noise dominated, so the SNR dependence flattens and longer T2 star plus short T1 allow more efficient readouts. Coffey and their collaborators pushed this further using hyperpolarized nuclei, showing that under special conditions, 47.5 millitesla can achieve SNR surprisingly close to 4.7 Tesla. That's obviously a special, precisely optimized use case, so not exactly what the swoop does, but it reinforces our main conceptual point. At very low B naught, SNR is not dictated by field strength alone. It's a balance of coil noise, relaxation timing, bandwidth, and sequence design, setting the stage for why portable MRI must rely heavily on optimized hardware and advanced reconstruction.
Moving on to AIM-2, this slide illustrates why portable MRI cannot use the same gradient encoding approach as standard clinical MRI. Clinical systems use large, high-power water-cooled gradient coils that can generate strong gradients and very fast switching, which is necessary to reach the edges of case space and achieve high spatial resolution. So in contrast, portable systems are size and power limited. The hardware relies on a compact permanent magnet shown on the left and tightly packed custom X, Y, and Z gradient windings shown on the right. These coils operate at much lower gradient strength and lower slew rate because there's no water cooling, limited heat dissipation, and a smaller amplifier power budget. So this directly limits the maximum case space extent, which sets a hard ceiling on spatial resolution. In MRI, spatial resolution is controlled by how far we can reach in K-space, which represents the spatial frequencies of the object we're imaging. The key equation here is that the voxel size delta x is equal to 1 divided by 2 times the maximum K-space value we sample. So if we can reach a larger K-max, we can get smaller voxels and better resolution. So what determines K-max? It's directly proportional to the gradient strength and the total readout duration, scaled by the gyromagnetic ratio. So increasing either the gradient amplitude or the time we spend encoding spatial frequency allows us to push further out in K-space. Portable MRI hardware limits both of these terms. The gradient coils are much weaker, typically 5 to 10 times lower amplitude, and because these systems run on low power, the readout time is shorter. Even if you wanted to extend the readout, the ADC bandwidth and slew rate are limited, so we can't safely reach high K values. The result is a fundamental upper bound in resolution. Portable MRIs simply can sample high spatial frequencies, so the images have larger voxel sizes. So this isn't a software problem, it's a physics limited based on the hardware design of these small systems. Here we compare typical clinical 3 Tesla hardware with portable low field systems around 64 millitesla. The key takeaway is that portable MRI has significantly weaker gradients and slower slew rates, roughly around 4 to 6 times lower G and 5 to 20 times lower switching. Lower B naught also forces shorter readout windows because SNR collapses and the coil becomes noise dominated. The combination of low G, slow DG by DD in short, it directly reduces K-space coverage, so Kmax becomes much smaller and spatial resolution hits a hard ceiling. This is why portable MRI cannot reuse standard clinical gradient encoding. The hardware limits K-space reach and sampling density before we even choose a pulse sequence. This slide shows an example, 50 microtesla portable MRI system using a Hallberg permanent magnet. Researchers built custom gradients in an RF system and performed 3D in vivo brain and extremity imaging. What's important is the resolution achieved. Brain volumes were reconstructed at roughly 4 mm isotropic and extremities at around 3 times 2 times 2 mm. Scan times were 10 to 15 minutes and required advanced reconstruction methods. Even with highly optimized engine in the system, which reaches a few millimeter voxel size, consistent with K-space limits from earlier slides. This demonstrates that portable MRI cannot reach 1 mm clinical resolution. With standard encoding, the hardware fundamentally limits K-space extent. So the key point is that clinical gradient encoding simply doesn't scale down to low-field portable MRI systems. Clinical pulse sequences assume large K-space coverage, which requires strong gradients and rapid slew rates. In portable systems, both G and slew are limited by the magnetic design, amplifier, power budget, and coil heating. So if we try to compensate by increasing the readout duration, gradients become nonlinear. The signal dephases and the system overheats. So even though the K-space equation suggests we could improve resolution by making readout longer, in practice we hit hardware limits very quickly. More importantly, at low B naught, the SNR is not body noise limited. Like in 3D, it becomes coil noise dominated. That means increasing the matrix size or pushing for more small voxels only adds noise without adding real information. So in AM3, we'll explore how modern reconstruction methods can overcome this constraint by exploiting coil geometry, sparsity, and learned priors.
Now that we've covered the physics constraints, we want to focus on what they mean for reconstruction. Low SNR, weak gradients, and inherently sparse K-space all combine to create a poorly conditioned encoding problem. In other words, the data we feed into reconstruction is noisy and incomplete, and the coil encoding is limited. When the encoding becomes ill conditions, sense becomes unstable because noisy coil sensitivities break the inversion step. Grappa becomes unreliable because noisy ACS lines corrupt calibration. And overall, we need much stronger regularization to get a stable image. The example on the right shows exactly why reconstruction matters. Conventional linear methods blow out the noise, while more advanced reconstruction can still produce clinically useful images. So next, we'll walk through specifically how SENS and GRAPPA breaks under these low-field constraints. SENS fundamentally depends on solving a linear system that uses Coy sensitivities to unfold aliased pixels. If that system is well conditioned, we can invert the matrix and recover the unaliased images. But when the matrix becomes nearly singular, as happens in portable MRI due to low SNR, highly similar Coys, and unstable noise covariance, you simply cannot invert it. That's what makes SENS unstable. The inversion step amplifies noise dramatically. The images on the right illustrates this. As the G factor increases from 1 to 4, the SENS reconstruction becomes progressively noisier, and by G equals 4, the method essentially breaks down. This shows exactly how ill conditioning leads to catastrophic noise amplification. On the other hand, GRAPPA avoids explicit inversion by learning interpolation weights from ACS lines. However, the entire method depends on ACS calibration being accurate. On top right plot, you see as the noise increases, the coefficient bias deviates from an ideal linear relationship. This means that as noise grows, the true signal has less and less influence on the fitted weights. Eventually, the weighting stops reflecting real Coy relationships at all, which is a very bad sign for reconstruction stability. In portable MRI, ACS and SNR is already low, so noisy calibration leads GRAPPA to fit noise instead of structure. That produces irregular, spatially varying noise and unpredictable reconstruction, as shown in the bottom image. Because the classic linear parallel imaging tools break under these hardware conditions, low-field MRI relies heavily on alternative reconstruction algorithms. Hyperfine's approach uses a neural network-based pipeline that bypasses the unstable SENS and GRAPPA steps, including case-based preprocessing, gridding, and patch-based denoising. Ensuring fidelity requires realistic, low-field noise modeling and self-supervised training, so the network only learns from the measured case base. Other methods, including iterative, model-based networks and fully self-supervised CNN reconstructions. To conclude, low-field MRI operates in a fundamentally different physical regime, not just high field but worse, short T1, long T2, star, and small and node. And weak gradients impose strict limits on encoding and resolution. Because of these constraints, advanced reconstruction, both regularized parallel imaging and deep learning, is not optional but necessary for portable MRI. Portable MRI succeed by balancing altered physics, hardware limitation, and robust reconstruction to deliver clinically meaningful brain images at the bedside.